Okay, I want to talk to you today about doing limits visually. So I want to remind you that when we say the limit as x approaches a of f of x is L, that means that if x is close to a but not equal to a, then f of x is close to L. Okay? So that's the key fact here we really need is that the value of f of a does not affect the limit of f of x as x approaches a. All right, so let's see what this looks like. Here's an example. Here is f of x. It's got all kinds of jumps in it, and now I want to ask about the limit as x approaches minus 3 of f of x. So if x is near to minus 3, then f of x is always a little above or a little below 0. So that tells you the limit of f of x as x approaches minus 3 is 0, but also when x equals 0, when x equals minus 3, f of minus 3 is equal to 0. So limit of f of x is equal to the value, so it's continuous at x equals minus 3. So the next most complex case, most interesting case, is at negative 2. If x is near to negative 2 but not equal, the value of f of x, the y value, is close to 1. Okay? So the limit as x approaches minus 2 of f of x is 1, but there is no value to minus 2. So f of minus 2 does not exist, so this is not continuous. Okay, I don't know what happened here, so we'll have to go back and forth. Sorry. The next most interesting case happens here at minus 1. If x is close to minus 1, but not equal, then f of x is, if it's a little above or below minus 1, then f of x is a little above or below 2. So the limit of f of x is 2, but the value of the function is 1. Limit at negative 1 is 2, the value of the function is 1. How about at 0? At 0, things get more complicated. If x is close to 0 but a little bit smaller, then f of x is up here around 3. If x is close to 0 but just a little bit bigger, then f of x is equal to 0. Numbers that are sometimes close to 3 and sometimes close to 0 are not close to a single value. So that means that the limit at x equals 0 does not exist. But also, the function itself does not exist, right? There is no value to f of x here. So in this case, neither the function nor the limit exists. Okay? So the only time the function is continuous is if the limit exists, the function exists, and they agree. All these other cases are not continuous. How about x equals 1? At x equals 1, if x is a little bit less than 1, the function is close to 1. If x is a little bit bigger than 1, the function is close to negative 1. And the value of the function is equal to 1. So the limit does not exist because there's no one thing that f of x is always close to, but in this case the function exists. Its value is 1, and that's very simple. And at 2, a similar thing happens, which is that the function is sometimes close to 0 and sometimes close to 2, so the limit doesn't exist, but the value of the function is 2. Okay. And I just want you to look at that picture and recognize that what this is saying visually about continuity is that if you can draw the curve without lifting up your pen, then it's continuous. Then the limit exists and the function exists and they are equal. If you could draw it, but there's one gap in it, when there's a hole in the picture, maybe the value is somewhere else, maybe it doesn't exist, then the limit still exists, but the function's not continuous. And finally, points like x equals 0, 1, and 2, where it jumps values, are called jump discontinuities. Those come up a lot in real life. The holes in the function come up in theory, but not in real life. But the jump discontinuities come up a lot. If you think about the current through a wire, when you flip a switch, it goes from 0 to some big number. You flip it again, it goes to 0. So those are jump discontinuities. We want to talk about those more, so we're going to offer some definitions. We're going to define the limit from the right and the limit from the left. We will write it just like a limit, except we'll put a plus sign when we want to approach a from the right, from above, and a minus sign when we want to approach a from the left, from the negative side. Okay? The limit from the right, limit as x approaches a plus, that means, again, if x is close to a, then f of x is close to L. But here, we only look at x that's greater than 0. So x has to be close to a and greater than 0 for it to be close to L. Anything could happen when x is negative. Likewise, the limit from the left, which we'll write limit x approaches a minus, means if x is close to a and less than a, then f of x is close to L. What happens when f of x is equal to or greater than a does not affect this limit. So let's return to our example, to our same graph. And now let's find in each, for a variety of points, the limit as x approaches the point from the left and from the right. So the limit as x approaches minus 2 from the left. We would look at the points x close to minus 2, but a little bit smaller, and look at their y values. Another way of saying this is put your hand over everything to the right of negative 2. So in that case, if x is close to negative 2, but a little bit less, f of x is close to 1, but a little bit less. But the same thing happens on the right. If x is close to negative 2, but a little bit bigger, f of x is close to 1, but a little bit bigger. So here, the limit is again 1. If the left-hand limits and the right-hand limits agree, then the limit exists. Okay? Which is what we found before. Now let's move on to 0. There it gets more interesting. If x is a little bit less than 0, f of x is close to 3. But if x is close to 0 and a little bit bigger, f of x is close to 0. Here, the left and right-hand limits disagree. That's the indicates you've got a jump discontinuity, and that means the limit doesn't exist. Similar thing happens at 1. As x approaches 1 from the left, numbers a little bit less than 1, their y values are close to 1. As x approaches 1 from the right, the numbers a little bit bigger than 1, their y values are close to negative 1. As x approaches 2, finally 2 from the left, we see that the limit is 0. Y values are close to 0. As it approaches it from the right, the limit is 2, because the y values are close to 2. So that's left and right hand limits, a little bit more of a refined version of the limits we talked about before. Okay, I want to add one piece of terminology to this, which I will illustrate by way of examples. Here is a function. Here is a function where the curve kind of shoots up to infinity and then shoots down from infinity all the way down to minus infinity, and then shoots down from infinity towards 0. In this case, if we ask what happens to f of x as x approaches minus 1 from the left, you can see the numbers are getting bigger and bigger, so we are going to describe that situation as it approaches infinity. Likewise, as x approaches minus 1 from the right, the y values grow without bound. So we will again say that f of x approaches infinity. Since the left and right hand limits are both infinity, we will say the limit as x approaches minus 1 of f of x equals infinity. Okay? So it's extending our notion of limit to include infinity as a possible value as if it were a number. But notice when we do that over here, things are more complicated. As x approaches 2, f of x approaches minus infinity. So I've said this backwards and I'm going to fix it. So as f of x approaches 2 from the left, the limit is minus infinity. But as f of x approaches 2 from the right, it's going up to positive infinity. Now, that's a jump discontinuity. The limit on the left and the limit on the right are different, so we say the limit does not exist. Finally, I just want to show you one picture that's hard to draw, but that illustrates one last piece about continuity. Here's a function where it's oscillating, and it continues to oscillate as it gets closer and closer to 0. So in this case, the limit as x approaches 0 from the right is perfectly nice, but the limit as x approaches 0 from the left does not exist, because these points never get close to any one y value. They keep jumping around different y values. Okay? That's another kind of continuity you can see visually, but it's a little harder to draw. Oh, sorry. So equal to 0, I am